in a circle around this point. So to decide where we cut it conventionally, we use the variational method, which is basically minimizing the energy approach analogy. And so integrating the tolerances in the model allows us to do some analysis with tolerances, other methods to figure out if our model works, and we can do some FEM based on tolerances, for instance. Then there's also another way to represent tolerances in the geometric model. That's the tolerance zone. So it looks like this. For instance, we have two types of tolerances, size tolerances and form tolerances, which have different volumes that work with the tolerances. And so you can directly tell the volume that works for both. So it's very visual. And then there is a third way, because we have problems with the two ways from before. The first one that we saw here, because it relies on points and position of points, you have problems with cylinders, for instance, that have vertices. And this is also very non-traditional, so that does conflict with the traditional practice. So instead, rational surface definition for a cylinder could look like this, where the tolerances are represented, for instance, with offset vectors. Then that was for geometry tolerances. Then we move on to what's interesting, the features, and integrating the tolerances as features. For our tolerances, we want to have many attributes like size attribute, form attribute, and position orientation. So, for example, if you have a feature that's this sheet metal crimp, we may want to specify tolerances on what's important. So the bend radius, the setback, the angle. So we may have this tolerances package with this feature. And another example, for slot, we may want also tolerances that's specific to this feature, like what's interesting for us. But then we may need, as the next step, we may need a clear structure that works for every type of tolerances. So we've seen this before with the last lecture from the professor, with the tolerances classified by size, brightness, and all the categories. Then I'll move on to the next part, design of assemblies. So when we have made our house in CAD, we then want to make assemblies. For instance, we made parts of a motor. We want to assemble this motor in CAD. And when we do an assembly, we want specific things. We want to allow to have the kinematics, to be able to to program the motion between the pieces. We want intentionality of parts. We want to rearrange the geometry and the parts as we want. So assemble is assemble, and we want to see where there are problems with collision and interference of pieces. So there's two ways of saying assembly. A top-down assembly where we decompose step by step the pieces, and bottom-up assembly design where we take each part and make the assembly. So that's how we usually do it in a CAD system. So what we want for assembly modeling is to be able to input hierarchical relations. So we want a part to be a part in another part. Matrix conditions. So that's how a piece fits into another and restricts its movement, restrict the degrees of freedom. And so that also to have to fix the components with the assembly positions. So there are multiple models, different abstraction levels. For instance, we could see this level with each part connected with its some subcomponent, but we don't have the geometric specifications. And we move on to the next level, which is where we specify the geometric mating conditions. For instance, we have these two parts, and if we want to assemble them in this model, we would have to this part, this plane, against this plane, another plane against another plane. So that's quite tedious, and that's a low level of abstraction because you have to have a lot of inputs. And the next level after that is with a higher level of abstraction, is where you don't have to do this manually. Is where you create an assembly feature that could be possibly for instance an insert feature, and then when you have created this assembly feature, you could say insert this into this, and it could automatically insert the pieces together. So that's an assembly feature, which definition is an association of two formed features that have different parts. So for benefits, obviously, you have to assembly creation at a higher level. That means less input and less effort from the user, and also it's also natural. And because we work with the feature parts, it supports design propagation. So, for instance, here we have an assembly feature that's called insert, as I said before. So we select these bumps and these holes, we could use the insert assembly feature to insert it. And finally, to conclude, I want to show you what's the current state of the this one. Okay. Okay. So that's under Katia, and we are in the sound. So basically, here the user selects the line that goes through the circles and another circles, and these basically tells them coincide, so they coincide. And then the users wants this plane to be faced against the other plane, so it selects the two planes. So you see, this is still a low level of abstraction. So we are not still at the level of take this piece and insert with this piece, and it does it automatically. So, but I guess you could program an assembly feature to do that if you use such an assembly often enough. So that's it for my presentation.
Once again, please include the address
Okay.
of video, YouTube video, showing on the slide. Okay. No questions. Oh, there's good.
14.
No, before.
Before the theme.
Before.
Oh.
Yeah.
This.
Yeah. How can VSM solve the problem of VPN and offset zone?
How can you solve these problems?
Yeah.
Well, that's basically why you use the directional service model. That's because we face these problems with the other models, so we use this instead, where with an array chain, we have offset on the origins, and we set it in the main dimensions. And what's interesting, I'll get you.
What is the D? D means?
The diameter of the
Variational VDM.
Oh. VDM is variational dimension system,
Dimension.
and this is a variational
surface. Dimension of surface. Dimension is one dimension. Surface can be dimension.
This is yeah, VDM.
Okay. 불빛이 나야 되는 거 아니야? 빨간 불빛이 나야 되는 거 아니야?
아니, 그렇습니다.
네? 빨로 쫓아가지 않게 하면 불이 꺼지는 거예요?
네.
사운드는 좋아하고 있어요?
네.
Right, so this is first part of chapter 6, manufacturing. Features in manufacturing. So we are already in the middle of the book, and I will cover only 1 and 2. Okay, and then manufacturing features. And some issues. Alternative approaches. Historical origin of CAD and CAM are different. So they are coming from far away and going in this direction. And meet again in the middle. Right? So CAD starts from computer graphics, visualization. And then drafting, 2D drafting, and also surface design. Surface design is for graphics. And CAM is coming from NC machine. And tools, APT is a programming language, automatically programming tools. Language for NC machine code. So they want to automatically move the NC machine. So there was a gap at the beginning, but now it's coming all together. Now they are saying it's one, almost one. So at the time, the data transfer between them was much difficult than now because it's far away. Paper drawings, so if it is not available, then you need to paper drawing, right? Design, printing, and handover. Paper. And then the CAM guys input again to the CAM system using paper drawing. That was the case, real case at the industry. Now we are trying to connect automatically and electronically. So CAM integration was a big issue in old days. Problem is low-level CAD models. What is a low-level CAD models? Can you name something? What is a low-level?
Graphical models.
My friend.
Yes.
But in a solid model, what is a low-level model entity? Geometric elements.
The low-level primitives like arcs, lines.
Yeah. Primitive is from CSG, so it's a cylinder, circle, box is primitive, right? But in the boundary representation, there are more low level. What is the lowest one? Point. Line. Face. Vertex, edge face. That kind of low level elements, graphical geometric elements, not useful for CAM. CAM, they are very specific to machining tool. Is drilling, milling, right? They have a discrete way of machining. That's all. So they want that kind of language for them. They are clear. Actually, let's show. Feature have been developed to help link between design and manufacturing. But at that time, feature in manufacturing was more advanced than in design. Why? Manufacturing, I just modified a little bit, so I come out later from this tool. Manufacturing features are clear and finite and corresponding to machining each. There are only not maybe 100 different machining methods, less than 100 machining methods. I guess maybe more, but finite anyway. Right? Because we need to have a specific machine to machine. Right? So it is discrete and finite and clear. Right? But in design should be very free. Right? I want to make a very new, conceptual, beautiful something, good and fast, and so it should be. Designers want to be. So you can think about the fashion designer. He's also designing, right? And food designer. Right? They want to be free, new, right? So it is not easy to formalize or standardize their terminology because they want to be free, new and free. That's why you can say ME is more advanced, clear, finite, and definition. area of feature-based manufacturing. That's why feature was grown from the machining side, and then used by designers. Because any designers start from very no conceptual, no early in the stage, very vague, fuzzy concept, and then arrive at it a little bit concrete and try out to make a model out of that. Right? Still, it's flexible. And then they want to link to the CAM so that they try to use machining features to convert their design into set of machining features. That was the way I move on. Right. So machining process, metal forming, testing, injection molding, rapid prototyping. It is a type of machining, manufacturing method, right? You may have a separate class how to manufacture. And also there is another category called inspection plan. Inspection, machining, and then inspection. And then also assembly planning. You just see that to satisfy requirement of modern manufacturing environments. So manufacturing features. Features can be defined from different viewpoints. Design feature, analysis feature, assembly feature, function, operational feature. Depending on how to use features in their work, they define different features. To the same geometry, to the same shape, they put different meanings because they work differently. Manufacturing features, collection of geometry. So still, you start from shape and geometry, but putting some meaning to that, particular manufacturing methods or process. Something like hole, slot, pocket, cutout, bend, weld, mechanical joints. Right. You see many simple one. To make this one, we use hole, box, and grooving, and pattern, and grooving again, and processing. And process and resource and parameters. And did I told you something like a PPR before? Yeah. In a factory, everybody talks about PPR. It's a three basic portion of manufacturing or factory. It's a product and process and resource. So already we have a process and resource. Product should be here, but it is about manufacturing. So product is object of manufacturing. Right? Manufacturing is applied to product. So they are only talking about process and resource. Resource is a machine, a robot, or crane, or material. And human is also a kind of resource in a factory. And then they manage the resources to make a process to make the real product. Process is something like an activity. So milling and drilling and facing, turning is very specific, elementary machining process. And for that process, we use machines, tools, and fixtures, and materials, and human. There's resources. Apply resources to the process. And then for that process, we need to have several parameters, something like speed of machining, speed of drilling, speed of drilling, 1000 RPM or 100 RPM or 10 RPM. 'em. 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 kind of parameters are needed. And through-hole is different way. Method 1 and method 2. Same twist dealing. Usually we do it this way, right? But sometimes we can use milling. Different way. Identification feature recognition, we already see this one. But here again, they focus on manufacturing feature identification. And then same, probably similar. Scope is only for pure machining, or it is for inspection, or it is for assembly features, or it is for material flow. Depending on the usage, you may have a different set of features. What we are trying to focus on here is machining. Right? Individual process steps, sources. Right? Process plan is between design and manufacturing or machining. You need to have a process plan. CAPP, computer-aided process plan. Process parameters, process sheets, parts drawing, and company standards. So then formalize process elements, process parameters, and relationship between process, and sequence, the steps sequence, geometric to process sequence, and then draw a generic sketch of each manufacturing feature identified. Now it comes to the identification of feature. And then finally we need to have validation. So I mentioned about history-free function in NX. Originally the technology is developed by another company called Synchronous. They adapt, NX adapt this technology to their including their system. So they are using feature recognition to make machine feature recognition. Okay, and the issues and alternative approach. There's a level of abstraction and level of specialization. Similar, right? Do you have any chance to expose to object-oriented programming? Yes? Object-oriented programming. No. Master student. Underrated. C++. Yes? Have you tried using C++? Okay. That is object-oriented programming. We need to know about class hierarchy. Class hierarchy. Hierarchy means tree. Tree. Top level class, bottom level class. What is the difference? General, specific. Tree. Or general, specific. Specialization, generalization. Or abstract or concrete. This is similar, very similar. Right? Higher, abstract and general. Right? Lower, specialization, concrete. And dimensionality, relationship between features, because there is an interacting features sometimes. Not independent. They are machining two cross group or temporal ordering, sequence, timing, and family. Level of abstraction. High level abstraction, up. It should be rough granularity, bigger size. Higher, general, rough, right? Features correspond directly to processes. Single chunk of process, big process. Count single as a one feature, what we call compound feature. Three-hole, bore, sink. Combine into countersink. low-level abstraction, low-level, smaller size, fine granularity, and that still it's a feature tree. High-level feature, low-level feature. Features represent a considerable variation of small shape and process. So there are a variety of steps also. Simply say this one is composite feature. One feature called countersunk core feature. But it can be divided into three different low-level features. Not so difficult. And then level of specialization, similar. And trade-off between generality and specialization. So you can use control. Stages of product development. So in the early stage, we should be more rough and bigger and abstract, but after lower level and afterward, we should be more finer and clear. Everything is going this way. And then feature-based manufacturing system. So machining features, and we need to have a feature feature recognition, and then abstract and concrete and special and general. So I put another example of abstraction level, general, special. Building is all the houses are a kind of buildings. But there is a special houses called detached houses, separate house. And then what is it? Henrietta's house. My home. My home. Very special, right? All right. Oh, this is very best. Okay. This final slide over. So, the top is very high level class, feature class, countersunk core. And then the generic process for this one is test drilling and annealing and concept. And then specialized variant feature type is a countersunk core of diameter probably radius 45. So more specific, one example something. Right? And then instance. So object-oriented programming, we used such a class hierarchy and finally instance level. Instantiation of class hierarchy, and then instantiation. So real numbers. Instance is a real number. My home is instance. Real world. But house is general. It's not real world. It's the abstraction of concept. Right? Okay, and then process sequence instance. This is process. This is something like a class hierarchy, and then we have processes attached to each classes. Right? Question? Yeah.
Professor, is there any effort to combine all the things related to a product? Are there any softwares like that are planning to bring everything at one point? In one software, like one software. Yes, product life cycle management.
Oh yeah, they are trying to do this.
Yes.
Now the Dassault and Siemens, they are merging all kind of companies, including finite element method, CFD, synchronous, and machining, CAM, PLM, IoT, bigger. Company is bigger. And technology is added. They are trying to make one single system and solve everything. I don't know whether it is successful, but the trend is this way. They are becoming bigger company.
I think digital twin technology, which is trending nowadays, is a kind of combining everything like product information and its life cycle, etc.
Probably. Right. Something new trend. Yes. We'll see that. I was also interested in digital twin too. But it's a new one, so you should keep an eye and then also involved in development in that technology. Question? And then maybe. Right? Your discussion, right?
Hi, I'm Hyebin Kim, and I prepare the discussion today. And my topics are design for clothing and AR, VR, and assembly. And first topic is design for clothing. As the clothing industry progresses, production CAD applications are becoming popular. So, in the past, in the past and present, design used the pen and pencil to design the clothing. But when the clothing is manufactured by the factory, they use the cascade stamp system. In general, the application is about the 2D drawing. So they use the clothing, and as the technology is advanced, the 3D modeling for clothing is progressing, proceed, and I find the research about that. First, they design the body shape of model, and depending on the shape, they uh, make the point and curve and surface of the clothing. So about that, they draw the clothing pieces, and also after the making the process, they use the animation of cloth. So when the model moves, they check the completeness of clothing design. So it's about the software for 3D vision design. So they use the clothing pieces, and they can revise and design them, and combine the pieces on the mannequin or virtual human model. So they check the shape of the cloth and they can change the color or texture. Of cloth. Finally, design. Also, there is an example of 3D shoes design. So they can revise the curve or surface of the shoe. Add the pattern or lines. Making contour. They also design the bottom of shoe, contouring the surface or line. And also they can decide in the shoes. And this is my discussion topic point about post-step or clothing design using CAD. Is it possible that clothing design using CAD can satisfy consumers' desire sufficiently? If it is not possible, why do you think about that?
I have a question. Is this only used for design so far, or have they manufactured using this sort of software with CAD? Only for design? I mean, not for manufacturing?
Including
Manufacturing as well? Oh. I think combined with generative design, it's very good for the clothing or shoe industry because many variants can be made. And then a customer can select which one they prefer, and then the company can manufacture that one. So,
do you think it is possible?
yeah, I think it's possible and a good idea.
Yes.
In the software, it looks tedious, where when you have to place every point on the model. So is there any feature like a sleeve feature or something that would shorten the duration of design process? Well, I guess point by point allows for more freedom, I guess, design freedom.
Sleeve is skinny.
Yeah.
Body.
Yeah. So another question is, can the design using CAD replace manual work slowly?
I don't think so. In the case of design, most of the work is produced by the designer's hand. And all we have seen that they have just used the image
Yeah.
in the CAD software, like in the case of shoes. So
what if it is possible to sketch directly to the software itself.
Yeah. But for that case, there are softwares like Photoshop and
I mean, then integrated to the CAD system.
yeah. But for the current stage, it does not have.
But the paper was from 2010, so maybe by now there has been some advancements, right? Maybe.
Maybe have you checked the price of such clothes?
Price?
Price.
You said they are manufactured and designed in
Yeah.
such software, so maybe not everyone can afford such clothes.
I, I have not thought about the price.
Maybe it's still okay for mass production. It's
Yeah.
for like generic designs.
But also the customization, like
Yeah. So the question is so
the
about.
body scanning, if there's body scanning, you can be sure that you won't have any problems because they are specially designed for you.
Actually, I want to share my experience with respect to this. I have worked in the shoe industry, so with respect to the shoe, first you make, first there is a development like the 2D surfaces, and then they are used, then stamping is used to cut down, and then they are like stitched and something like that. I think so that in the case of clothing, there would be a total dedicated factory or machine that automatically uh, stitches the patches of cloth. So if we are making one cloth from the one design, then it will be expensive. But we are using that software for mass production, then it will not be a problem.
About one design.
Yeah.
So actually, my third question is, could it be helpful for customization?
Yeah, it has a big scope for customization. As Professor said that if we can combine the scan of the body, then we are sure that.
But how you will produce the customized product? It is good up to design stage, but when it comes to the production, it will be limited.
Like size?
The machinery maybe.
Because when you have to cut something, it has a specific die for it. For every design, for every shoe design, there are almost 20 dies that cut the leather.
Maybe if the machine tool can have the algorithm about the design,
Variation.
is it possible to? No.
But I think that customization is all about taking into account the different sizes and getting to fulfill the variation.
Or you can have pre-filled customization, like those are the options that you can select. Then it's possible.
I think in the future, if 3D printing goes to the level where it can print cloth, fabric, then it can be a very good product for the general public because many people can design and print their own clothes at home. I guess they won't have the expertise to design, but it's a fun experiment, I think. I would like to design my own clothes.
That's good.
Okay.
Any other opinion? And I move to the next section.
Before then,
Yeah.
please go to the YouTube and then find out Adidas speed factory. Go to the YouTube. Mm. Speed factory. Speed. Sound. 저는 they scan the food, and the robot is sewing. And bottom is 3D printed. They want to we can find out more later.
My second topic is AR, VR, and assembly. And the assembly is the fundamental function of CAD system. The more complex machines, the more important is assembly of parts. So you already know that. And there are application of AR, VR for assembly. So that side is the assembly in VR. So they can simulate the assembly before manufacturing or installation. And right side picture is the assembly in AR. So AR told them the direction of assembly. So It is about the AR assembly demo. They use the 3-point set for tracking the real model. They can track the orientation and position of model. The software it shows the parts for assembly. When they change the orientation and position, the tracking can so and this is about the video actually 4.0 about AI. Good.
Physical realization. With our or augmented reality apps, we meld both worlds, and this is what it looks like. To meld both worlds, you need a registration, physical to virtual world. To get this registration, the user has to know the virtual part that he sees in the real world and place it similar to the real part, just like this. And as you can see right now, it snaps automatically into its position. And from now on, we have a registration in both worlds. And now we can switch between them. For example, for analysis aspects like this.
And my discussion point is how about the assembly between real part and virtual part model? Is it possible or not? Why do you think about that? And if it is possible, what are the pros and cons?
I think it's pretty possible because, as we saw with the Elon Musk gesture thing or with the sandbox, AR is becoming more advanced. So, and I think I've always believed that AR is very good for assembly purposes. Maybe not for general CAD designing or anything, but for assembly, I think it's very good. So I think it's possible, but maybe currently it's not very robust. Like we saw, it's very glitchy, many problems, and also takes time. So maybe currently it's not a very useful application, but maybe in the future it will be better.
I think it would be good for training the workers, for training before getting onto the manufacturing the chain, the production chain, so they can get used to instruction without distress. So I think it would be very useful for that.
For both cases, do you need to first export the model first to the program, like somehow. Because I don't think the AR program creates the model in real time, the 3D model. Right? So do you need to export it to the AR program first? Export the model from your maybe CAD program.
I said the real part is the existing object or creature, and we assume we need to, for example, a real part is one of the boards, and we want to make the node or virtual part model. So we before manufacturing, we want to check the assembly of existing object and the node. So I think about.
He was asking that when you make the virtual part model, do you have to first make a CAD program, CAD model of it, and then export it into virtual the environment, or is there some instantaneous way of exporting? Like, I think in the Mercedes factory video, they do instantaneous exporting, right? Didn't it look like that?
Yeah, like it kind of scanned.
Yeah, it just scanned and
But
then.
the previous one was the virtual parts were built inside the system. So there are the two kinds of things. I think that this application is good for the industry, but providing layer at the very user level is kind of difficult. Don't you think?
We do not have enough technologies to use AI for tolerance evaluation. Because in the case of tolerance, it is very small dimension changes. So maybe it is not possible with the given technology.
As you said, for your purpose by checking for assemblies, I don't think if you only use it for that case, I don't think there's the advantages outweighs the challenges you need to face with this. We can just check that through the 3D model maybe. So maybe if you want to justify using this, maybe like Alex's example, it's for training workers, or maybe to check how it works in the real world or something.
Maybe if we apply this to your first discussion topic about clothing, maybe it's good application because real part is the human and they just check the virtual clothes. Yeah, it could be.
So to realize the assembly between real part and virtual part, what technology do we need?
I think
Scanning.
A faster computer.
I think a dedicated virtual environment for like this. I mean, it will be then similar to the first video, but yeah, there can be different kind of ideas. Like you put the part in that facility, so the system automatically checks, but you have to give the virtual part as input to the system first, so that it has an idea that what kind of, like I am also working in the it's not fully automatic, something it's based on the voice recognition. So what I'm saying is that there can be an evaluation of the candidate entities, like candidate matching parts, so that can ease the
Sunday to 22 volts.
Any other? No? This is the end. Thank you for discussion.
Okay. Okay. That's it. See you then Monday.